All right, we're going to continue our RTDSP Project 4 demonstration. So in the first section, we talked about just implementing basic IIR filters in System C Code Composer with this example tutorial for part 1. Now in part 2, we're going to do our first application of an IIR filter, and we're going to design a notch filter. Now we designed a notch filter using an FIR filter by just simply shaping the frequency response to look like a notch filter without having to know the transfer function. Well, this time we're actually going to develop the transfer function for the notch filter and create an IIR filter from that transfer function. So this is the transfer function of the IIR notch filter that is observed in the lecture. So it has a notch frequency, which is going to be omega naught, which is 2 pi times the frequency of the notch frequency. It has a band, a reject band. So basically what frequency is around the notch frequency that will also end up getting attenuated, because the notch filter generally has a small bandwidth of rejection to generally reject frequencies only around the notch frequency while leaving the other signals unattenuated. So this value will be small, and the notch frequency, or the bandwidth of rejection will be small, and the notch frequency will be whatever we decide to design it as. So with this transfer function, it's in the S domain. So there are two ways to obtain the IIR filter difference equation. We can use from the transfer function in the S domain. We can either use impulse invariance, or we can use bilinear transform. Impulse invariance is the longer method, but is longer, but can sometimes be more accurate than the bilinear depending on the circumstances. So the impulse invariance method requires us to transform this transfer function from the S domain into the T domain using the reverse Laplace transform. Then in the T domain, it is sampled to the discrete time domain, and then from the discrete time domain, it is transformed to the Z domain using the Z transform. And then from the Z transfer function of the Z domain, we can then extract the coefficients for our IIR filter from the Z domain. So we're going to go ahead and start with the impulse invariance method as I just described. So the first thing we have to do is transform this using the inverse Laplace transform for the time domain. Now, the first problem we see right off the bat is that the order of the denominator and the numerator, or the order of the denominators, is not greater than the order of the numerator. So we have to do a bit of work. So I can factor out an S over here, and so that way this is so that the denominator's order is higher than the numerator. Of course, this S will come into play later because this will count as differentiation, but we'll get to that later. So I have this, but now I also want to complete the square. So in order to complete the square properly, I set this up, but with this S plus another value, I want to match that in my numerator. But if I'm going to add an S times an omega C over 2, I have to subtract 1 as well to keep everything balanced. And this value has remained the same. So with this, I have essentially three parts, and I now need to perform the inverse Laplace transform on all three of these parts to get the time response. So we're going to start with this first part over here. So since I've matched this, I can set alpha equal to omega C over 2. That way I have S plus alpha. And I can set beta equal to the square root of this value, so I can get beta squared. This puts it in a nice form that can be easily reverse Laplace transformed into this, but this extra S in front counts as it gets reverse transformed into a derivative. So then I take the derivative. So this H1 becomes H1 of A, which is where I take the first part, where I take the derivative of this term and leave these two terms the same. And then there's the B part where I take the derivative of this term and leave the other two terms the same. And then H1C, which is where I leave the first two terms the same and take the derivative of the last term. And so the derivative of the step function is the delta function. And so then I have to sample. So sampling basically means that I take a sample every sampling frequency. So I can convert T into NTS to all of these for all my time functions, and I can make this transformation to help me write these discrete time functions in a form that's easy to Z transform. So once they're in this form, it's easy to see the Z transform by using the table. And so then I can Z transform each of these separate equations and each of these equations will then be added together at the very end. But for now, I'll just leave them in these separate forms because I have the next part to do. So the next part, if you remember, is going to be this part right here. So for this part, again, since I have completed the square in this way, I have s plus alpha again, and then I have this beta squared over here. So then to get into a form that's easy to do inverse Laplace transform, I multiply and divide by beta. I just keep this as a coefficient in front. To multiply, I take this reverse Laplace transform. I sample it, basically setting t equals to n times the time step. I rewrite this in terms of a, because this puts it in a form that's easy to z transform, and I have this k, which is this constant in front. So then I can easily z transform and obtain the z transform. So then the last part, which is going to be this negative s plus omega c over 2 that we had to add, that we had to subtract to balance the additional one over here. So from this, I already had it. No, I guess I should have. I guess got a bit too hasty here. I should have just left this for now as omega c over 2. And then I'm going to perform these transformations. I'm going to get alpha, I'm going to get beta. So we alpha, I'm going to get beta. So then I multiply and divide by beta to get this form over here, while leaving this alpha as a coefficient along with this s. So this is a form that's easily to reverse Laplace transform. So I reverse Laplace transform this. I have this a over beta still. And I also have this s, which turns into a derivative. And then I just need to form the derivative, but I have to form the derivative rule for multiplication. So then I have three terms. I should have this term, where I take the derivative of the first number, leave the other two the same, take the derivative of the second term, leave the other two the same, and take the derivative of the third term, leave the other two the same. And remember, the derivative of the step function is the impulse function. I can sample this by taking t equals to n times the time step. So then we notice that since this is a sine of 0 is going to be 0, so this value is basically 0. So I'm left with only this top part left. And then I rewrite this in a form that's easy to transform to the z domain. So then I form the z transform, and I have this function. Now from here, I just have to now combine all the parts together. So I basically combined all the parts together and did a bunch of algebra to rearrange everything. So that way I had everything. See, this is like z to the 0, and then this is everything in here is z to the -1. This is z to the -2, and so this is z to the 0th and z to the -1. I have it in descending order to make it easier to derive the coefficients for my IIR filter. And so then I also add the scaling factor based on the sampling frequency of the transfer function. All right, so with that theory out of the way, we're going to talk about it in MATLAB. So in MATLAB, I have the sample frequency set to 48,000. So I'm going to set my notch frequency to 500 hertz right here. Seen right here, 500 hertz. And I have my bandwidth at 50 hertz. So the reject band around 500 hertz is 50. And so then I first need to generate the impulse invariance and the bilinear response, so that I dump them into the C++ code. I dump them into C files and out of Red and Code Composer. So for the bilinear transform, I basically just use a coefficient matrix. So like for the numerator here, this matches the coefficients of the numerator of the bilinear. Oh, I didn't talk about the bilinear transform, did I? Oh, let me talk about the bilinear transform in theory first before we begin. It's relatively brief. The bilinear transform is a lot simpler than the impulse invariance method. All I have to do is perform this substitution of s equals 2 over the time step, multiplied by this quantity, then rearrange everything to put it in a form that you can easily extract the IIR filter coefficients. The bilinear transform, so just like how the impulse invariance method, you can't design high-pass filters with it. So that's one of the limitations of the impulse invariance method. One of the limitations of the bilinear transformation method is that the bilinear transformation method loses its linearity as you approach the sampling frequency's Nyquist frequency. So the sampling frequency must be much larger than the frequencies that you want to work with in order to use the bilinear transformation. So with that, just by applying the algebra, I've acquired the transfer function using the bilinear transformation, which is a lot simpler than using the impulse invariance method. So going back into implementing these, what we did in theory now in MATLAB. So we'll skip bilinear. We'll start with impulse invariance since I started with the impulse invariance theory. So the impulse invariance function is right here, and basically these just correspond. So this fs minus 2 alpha is this term right here, and this is all in like an array or a vector, or coefficient matrix, whatever you want to call it. And so this is this middle part, this middle term over here, and then this is this last term over here. So this is the numerator coefficient matrix, and this is the denominator coefficient matrix, 1, negative 2, cosine beta, and then alpha, or A. And so from here, all we have to do is we extract the feed forward and feedback coefficients from the numerator and denominator. So the feed forward coefficients are the same as the numerator coefficients, but for the denominator, you have to subtract it and you have to scale it by, right now the scaling factor is 1 because it's scaled based on the first term in the denominator. So in this case it's 1, so there's no real scaling, but you have to take the negative of those denominator coefficients. This gets us our impulse invariance, feed forward and feedback these are the feed forward and feedback coefficients that we'll write into C. So for the bilinear transformation, just like I was talking about earlier, it's a lot simpler. You just perform this substitution and then do all the math necessary. So this down here is what I've implemented based on all the algebra. So you see this K2s, which is K squared plus W notch squared. And then all these coefficients are inside this coefficient matrix. And then in the denominator. And so then from this coefficient matrix, we have to do some scaling. So this time the scaling is not always going to be 1, or the first term of the denominator is not always going to be 1, so I have to generate the scale value. So I scale the numerator and I scale the denominator, and I always have to subtract the denominator coefficients to get the feedback coefficients. And so then I just simulate and output these coefficients. So this is basically all that the MATLAB code does, is implement what we've just discussed in theory, generate those coefficients, and write them in C. So if I run this real quick. All right, so we have this. So we're going to talk briefly about what we got over here. So the impulse invariance method, we see that we have a notch at 500. So if I go up to about, so at 25, I have a dB of negative 0.48. And if I go up to 50, it's about negative 0.78. So it doesn't actually approach 1, or at least close to 1, until probably around, I guess we could call it 600 might be a good rough estimate. Similarly, this is for the impulse invariance. Similarly, for the bilinear transform over here, at 500, the gain is very low. And then as we step away from the notch frequency, the gain goes back up. So yeah, approximately probably around 600 again, you'll stop noticing the attenuation. So these are what these look like. So if you're wondering what these are basically simulations. So I've simulated a sine wave at 500 hertz, which is at the notch frequency. So as you can expect, this gets attenuated down to 0. And so then notice how the magnitude of the frequency response is very low because it's all been attenuated. Similarly, this is another simulation, but this time we're going to simulate, because the previous one simulated the impulse invariance. This one will simulate the bilinear transform. This is the binary transfer response. It's pretty much the same. It's going to get attenuated to 0 because it's in that notch frequency. So let's go ahead and look at it in Code Composer. So in Code Composer right now, let me just close this out. So right now I'm at the notch filter at the impulse and variance method, or impulse and variance coefficients. So if I go to the DSP configurator, I make sure my sampling frequency matches. I can look at what my coefficients are. So notice the IIR filter doesn't generate as many coefficients. So even though this is a notch filter, this only generates like 3 feed-forward coefficients and 2 feedback coefficients. While for when we did the FIR filter for the notch filter, we had to use hundreds of coefficients, or as many as possible, depending on the sampling frequency. So that's one of the advantages of IIR filters, is they use a lot less coefficients. And that's a good thing, because if we look into my IIR filter code, and so I have the order, second order, I create the buffers, I take the input stored in the first cell in the buffer, I perform the dot product using a loop. But this loop right here, this is to shift the buffers. And notice how I don't use a pointer. Instead, I use a shift register, and that's because I have not taken any advanced C++ classes, only the introductory C++, and I'm not too familiar with advanced C++ concepts such as pointers. So instead, I implemented it using a shift register. But the shift register is not as efficient as we discussed earlier in Project 2. But luckily, I don't need to be as efficient because I don't need to perform as many calculations. And I don't need to perform as many calculations because the number of coefficients I'm using is a lot less thanks to the IIR filter design. So that's one of the benefits of the IIR filter. With fewer coefficients, I can afford to be less efficient about shifting the register without any drawbacks. So this shifts the register, and then this is the output, and then we display the output on the speakers. So if I go ahead and if I run this through debug, let this run. All right. Come on. All right. So we can take our, let's take 1,000 hertz signal. So for the 1,000 hertz signal, you can hear it. It passes through no problems. And then if we take the 500 hertz signal, notice how it gets notched. You don't hear anything. I can turn up the maximum volume right now, and you might be able to barely hear it with maximum volume. So that's with maximum volume. So if I go back to maximum volume with the sine wave, you can hear it very clearly. And if I wanted to use a lower tone, so if I use a lower tone here, you can hear the lower tones as well. It's only that 500 hertz frequency signal that got notched, because that's how our notch filter was designed. So that shows that our notch filter is working clearly. So this was with the impulse response. So next we're going to do the bilinear transformation with the notch filter. So if I just close out all these files from the impulse response, impulse and variance, I can open up the coefficients, open up the DSP header. So the DSP header, again, I have it set to 48,000 kilohertz. The coefficients, there aren't very many of them. There's only, again, there's only 5 of them. There's 3 feed forward and 2 feedback. So with such few coefficients, I'm allowed to be less efficient with my register, which I am, because this code is exactly the same as with the notch filter for the impulse response. I still have the same buffers. I still store the first value. I perform dot product, and then I perform feedback, or not feedback. I start shifting the register. But when I shift the register here, I use a shift register because I'm not proficient enough in C to confidently use pointers. So we're stuck using shift register. But like I said earlier, since the IIR filters have fewer coefficients, I can allow myself to be less efficient with my register and not suffer any consequences, unlike with the FIR filter, where every calculation matters to get the most accurate filter. So we're going to run this again. Well, I guess not run this again. We're going to run this with the bilinear transformation coefficients instead. So with this, all right, it's waking up with that. All right, so we can put in the 1,000 hertz signal, passes through no problem. We take the 500 hertz signal, it's attenuated greatly. This is at max volume. You can hear it slightly, but it's very dull. It's very attenuated. And I'm going to turn down the volume a bit so I don't blow my ears off when I switch to a signal that's not attenuated. So we can take the 2000 hertz signal. 2000 hertz is definitely not attenuated. So I take the 200 hertz signal. Yep, definitely passes through. I can take the 300 hertz signal. Passes through. Everything passes through except the 500 hertz signal because that's at the notch frequency. Here's 1000. So they're all passing through except for this 500. So again, that shows that this filter is only notching around the 500 hertz frequency. So this means that our notch filter was successfully implemented using an IIR filter instead of an FIR filter. And as I discussed earlier, the benefits of the IIR filter are that you use fewer coefficients, which is great for me because since I don't know how to use pointers very well in C++, I can get away with using a shift register without sacrificing efficiency because I don't need all those taps like with the FIR, all those calculations like I did for all the taps for the FIR filter. So that's definitely a benefit of the IIR filter design. Now the drawbacks of the IIR filter design are basically what I did in the first part of the video, all the theory involved with IIR filter design. So if you remember what we did with impulse invariance, required a lot of theory and a lot of reverse Laplace transform and rearranging the equations to be easy to transform into the different methods. The bilinear transformation is a lot simpler, but you still have to do a bunch of algebra to get everything into a form. You still have to do a bunch of algebra to get into a form that you can extract the coefficients from. So while the FIR filter might require more time, more calculations, more taps, it is a lot simpler to design. While an IIR filter uses less coefficients, but requires more work to design. So those are some of the benefits and disadvantages of IIR filter versus FIR filter. So that's going to conclude our discussion or demonstration on the notch filter. As I showed earlier, notch filter can successfully notch only a specific frequency while allowing the other frequencies to pass through. In the next video, I'll talk about the cascaded bandpass filter using RC filters. And just like with this, we'll start with theory and transfer functions and discuss the impulse invariance and the bilinear transform and all that. And then we'll move to MATLAB where I'll generate the coefficients. And then I'll demonstrate in C using Code Composer Studio and download it to the DSP board. So we'll save that next part for the next video.